Right. Okay. In the previous session, we discussed about the components of the vectors, right? And basically, we identified that we can take a force or any kind of a vector, right? It may be displacement, it may be force, and that can be split up for two separate components, the vertical component and the horizontal component. And there we have to, with the given angle theta, if the component is adjoining with the theta angle, we call this one as a force, or this may be a displacement or meter value, right? Multiplied by the f cos theta, the other side automatically become f sin theta, right? So this process is called as a resolving the vector. And also we discussed several questions regarding that, especially when the forces, you can see in here, this is a forced simple diagram for a trolley on a ramp, and with the sloped flow, that angle is equal to this angle. And what we can do in this case is that if I mark the forces here, the weight is here, and this is the result, the reaction force, so the R force. And if the trolley is moving in this direction, this should be the friction. Then I can simply, what I can do, I can resolve this weight of the object into two separate components like this. Okay. Then I can forget about this weight. Now I can add this one to F some equal M equation, and if I consider one direction, then I can basically put whatever the value, and I can easily solve the question. And we discuss simple example that when we resolve a force, what happened? When we resolve a force, the force value is actually increasing. So that is going to be an issue, right? So it is very easy to move the box when the rope is horizontal. Let's say this is 5 newtons. And when you apply it with an angle, it becomes much larger, right? So we discuss about several resolving questions, right? Now, for today's lesson, we'll start with the center of gravity, why it is important, right? Since we have a weight, because the force of gravity on the earth on us, and each part of our body, whether it is arm or leg or head, all of them experience a force caused by the force of gravity. Okay. However, instead of going for each and every part of our body, we can just consider a single point where overall effect of the gravity acting as a single point. This is called as a center of gravity, or also simply you can say the point where all the weight of the object may be considered to act. Right. Now, when a person is standing upright in a normal situation, center of gravity is roughly in the middle of the body, right? However, you can see this athlete actually perform a high jump, right? During this performance, you can see a dashed line, right? Here it is the dashed line. Now, this dashed line actually indicate the path of the athlete's center of gravity, right? It is a smooth trajectory through the air, right? Okay. One practical thing we can learn of is how to find the center of gravity. You can see this is a solid body, however it doesn't have a regular shape. Okay, I mean, for most cases, for example, for most cases, if we have some kind of a wood block on top of a table, then I can take out the symmetrical center of this wood object, and this automatically become the center of gravity. Yes, the symmetrical center. However, in a regular object case, you can see we cannot guess it, right? We cannot guess it, and there's no symmetrical shape. In that case, you can take a plumb line, right? You can pick up in three different points, right? Then you can apply this plumb line in each direction, right? If you apply it in here, this is the path. Then you can mark it. Then you can pin it in here and you have rotate it. Then this is the path. For this one also there's a path. And the intersection we can easily identify as the center of gravity. Right. Then we'll move on to the next part of our lesson, right? We have to learn about the moments, force moments, right? Force moments. Right. So far, only we have discussed about linear forces, right? We learn about linear forces. What I mean by that is that we always talk about the forces applying in a certain direction, right? It may be left or right. It may be up or down. However, this momentum, force momentum, we have to consider when the forces are, when we can apply the forces in rotational way, rotational direction. You can obviously see, here you can see, this is the center of the nut and we are using a spanner, and the person is actually applying a rotational force like this, right? In this direction with the hand. Then what happened? Based on the center of this nut, it is rotating into the right hand direction. And it may be, if you put the force in the other side, other way, opposite side, it is in the left hand side. However, in the force momentum cases, the technical term is not about right side or left side. We call this one as clockwise and anti-clockwise, right? Clockwise is the side where the clock arms are rotating. The anti-clockwise mean basically the opposite side, right? I think it is very easy to remember. Clockwise and anti-clockwise. We'll use those two terms, okay, for the rest of the lesson, right? So as I discussed, the difference is we are talking about the rotational applying forces, okay? Basically, applying that force, you can make an object turn around, right? For example, fastener with the threaded hole, right? Using a spanner to loosen a nut. Okay. And if I ask, if I want to get the maximum result, maximum turning effect with the use of this hand, what is the requirement? There's actually one requirement that the operator or this handyman pulls close to the end of the spanner, right? You have to pull it close to end of the spanner, which means from the center of the nut, and you have to take the farthest point, furthest point. You have to go for the furthest point, and there you have to apply the force at a 90-degree angle to the spanner. Basically, it means this, right? Here is the center point, and this is the length of the spanner. You have to apply the force at the furthest point with the angle of 90 degrees. This should be 90 degrees. This is where you can have the maximum turning effect. Right? Remember, another good example. Whenever you are opening or closing a door, this is the same effect, right? You can easily open a door. You can easily open a door. Let's say this is a cross section of a door. Okay, then here we have that lug nut, right? And this is the door handle, right? You might find that if you use the door handle, actually it is very easy to open or close a door. However, you can practice this one. If you go for the nearest point, near to the this rotation axis, you might find it is very hard to open the door, right? So this is much easier. This is much harder, right? And also it is very easy if you apply it in a 90-degree angle. Otherwise, if you apply it like this, what happened? We have to resolve the forces. When you resolve the forces, the force magnitude automatically become larger, right? Right. Now we'll cover the moment of a force, right? The quantity that tells us about the turning effect of a force is called as its moment. The moment of the force depending on two quantities actually. You have to thoroughly remember these two quantities, okay? Actually, these are the requirement to calculate the moment. Very, very important to remember correctly. First of all, magnitude of the force. What is the force value? If it may be 1 Newton, 2 Newton, right? And you can say the bigger the force, the it it makes the greatest its moment. And second one is perpendicular distance of the force from the pivot point. Then that is the second quantity, right? Remember this term. This should be perpendicular distance of the force from the pivot point, okay? Right. And you might see that further the force acts from the pivot point, the moment become much larger, okay? And now this is the equation to calculate the momentum. You have to multiply the applied force multiplied by the perpendicular distance of the pivot from the line of action of the force. Okay, so it is the same two things. Force, the perpendicular distance from the pivot point from the line of action of the force. So let me talk about the line of action now. Right. Okay, in this figure you can see, yes, in this figure you can see, right. Okay, this is the pivot point, yes, and you can see this is the applied force, and line of action of the force is this one. If you draw a dash line like this is the line of action. And what is the requirement? From the pivot point perpendicular to the line of action of the force. which means I have to get this distance, right? I want to know this distance. However, in certain cases, some people misunderstand this one like this. For example, look at the next figure, right? Look at the next figure. You can see this is the pivot point. However, the force is applied in this direction. Line of action is in this direction. Then people always confuse, okay, this is the line of action distance from the pivot point. Actually, this is wrong because we have to take the line of action further and take the perpendicular to that value. Then this is the correct value. This x2 represents the correct distance. So you have to multiply in the first case f1 multiplied by x1. In the second case f2 multiplied by x2, right? So how to get the x2 value then? How to get the x2 value? You can resolve the forces, right? You can resolve the forces. Since it is a triangle, a perpendicular triangle or right triangle, yes, you can use the Pythagoras, or you can just take the value as d cos theta, right? So since we are talking about the vector resolving, right? Then I can take this distance d, because of this angle, I can take it out as d cos theta, right? Yes. Or is it? Is it d cos theta or d sin theta? If this is d, if this is the angle, how to find out this one? It is for the angle, this is the opposite, which means this is a sine. Yes, and this is the, okay, the largest side, which means the, okay, we had to use the sine here, right? And then I can write down sine theta is equal to the unknown length x2 divided by the d. Then since you already know the theta and d value, we can take out the x2. So x2 is equal to d multiplied by sine theta, right? So whatever the d distance, let's say 10 meters, 10 meters, sine, let's say sine 60, then you can take out that x2 value. F2 is also given. You can just collect the moment, right? It is as easy as that. Okay. Now, considering the pivot point position and the applied force, can you identify whether it is a clockwise direction, clockwise, or is it in the anti-clockwise direction? So in the first scenario, it is clockwise direction. Second one is also clockwise direction. However, if I put a pivot point like this and apply the force like this, what is the direction? This is the perpendicular distance. So this is also clockwise direction, right? And if the pivot point is here, if the force is like this, it is again also the it is also in the clockwise direction, right? And since the moment is a vector, so you should have as a force, similar to a force, you should have the magnitude as well as direction, okay? So for the forces also, we mentioned the value is 20 newtons with the arrow depending on the direction. So for the moments also, you should give the value. So what is the unit of the moments then? If this is the equation, can you find out the unit? It is obvious, right? Moment is equal to force multiplied by perpendicular distance from the pivot, which means, so basically force means newtons, distance is in meters, Newton meters. And in the actual representation, you should be able to provide either like this, either you can write down clockwise direction or anti-clockwise direction, or otherwise you can just put a the arrow like this, right? Whether it's anti-clockwise or clockwise. Only one, okay? Only one into one direction. Don't put the same direction in both sides. So Newton meters is the unit of the moment of a force. So we discuss, even though there are two methods, we just discuss how to find out that x2 distance, right? Since it is always, we have to consider perpendicular right triangle is always present there. You can just find out whether is it sine theta or cos theta. You can easily find out. Now, the most important point of learning the moments is you can in every object, for any rigid object, you can find out whether it is balanced or unbalanced. You can determine whether any system, a rigid system, is balanced or unbalanced. Now, up to this point, we have discussed with the Newton's laws, very simple diagrams, right? However, now since we already know the theory of the moment, we can apply it to uh, rotating systems, rotating masses actually. Any system contains of rotational, or whether if there's a pivot point, right? In that case, you can see for this example, on top of the pivot point, there's an rigid line, and it is actually balanced. There are two different weights, supposed with different distance from the pivot point, and we can check whether this system is stable. Okay, this is stable in the sense, as a term in the force lesson, we call this one as equilibrium. Right? Whether the system is in the equilibrium position, right? Okay, we don't say the stable, but we say the stable or equilibrium position, which means it doesn't move in, it doesn't either, if there's no movement, or it can be rotated in a uniform velocity according to the Newton's second law, right? If there is no external force harassing the system, the force is either, so system is either no velocity, which means it is not moving, it is in equilibrium, or it can be in equilibrium with same or uniform velocity, not acceleration. Okay, if there is acceleration, the body is in the movement. Okay, right. Right. So how to use the moments to solve this kind of a question, right? First of all, we can check two things, okay? Check whether an object will remain balanced or start to rotate. So in this case, what do you think? In this shown figure, is it in equilibrium, or is it balanced, or will it start to rotate? I think, I believe this is going to move, right? I think it is this object, let's say, I don't know whether correctly, but there are two different weights in two different distances. If it is in the same distance, let's say this is 1 meter and this is also, let's say this 20 newtons is also here, I can definitely say this is going to move because here it is 40 newtons, here it is 20 newtons. But we don't know whether it will start to move. And second one is calculate an unknown force or distance if we know that an object is balanced, right? You have to find a unknown force. In this case, in this free body diagram, what is the unknown force actually? There's one missing force. The weights are also there, and since this pivot point has a reaction force in the opposite direction, it should be marked like this. Now, this is the unknown force. Now, this force diagram is complete. We don't know this value, so we can just put it like, let's say, P force. We don't know the reaction. Let's say R. We don't know the R. We'll try to